my name is Christopher Siefe, and I'm going into my second year as a chemical engineering major here at UCSB. I'm currently working as a part of the Moskowitz Research Lab under the mentorship of Jose Navarrete, and today I'll be giving a presentation on gate-tunable plasmonic devices. So first off, what are surface plasmons? So surface plasmons are electron oscillations that occur in metal at the nanoscale level due to electromagnetic waves. And so you can see here how the electrons in the metal oscillate with the oscillating electric field of light. And although we've known about these surface plasmons for a great deal of time now, there's still a lot more that we can explore with them and see how we can tune them to our own benefit. And so the benefit of that new knowledge is that we can apply it to various devices, such as this solar water splitting device, which utilizes surface plasmon resonance and sunlight to split water into hydrogen and oxygen gas. And so this device in particular has a lot of great advantages in that it's a very clean way of storing energy in the form of hydrogen gas. But in addition, we can apply surface plasmons to other processes and drive other types of reactions, as well as utilize surface plasmons in applications in photonics, photovoltaics, as well as catalysis. Namely, that last one, we hope to, from a continuation of my current project, utilize these surface plasmons in addition to a nano device to kind of control the catalysis of a reaction, essentially allowing us to tune the catalysis under sunlight by changing the voltage that we apply to this device. But so for now, my current project, and our current project, is to incorporate a tin oxide nanowire covered with gold nanoparticles into a nano device. And so the idea behind this is that by using this device, we can kind of indirectly sense these surface plasmons and learn a little bit more about them. And so by shining light on this device, like you see here, we can cause surface plasmon resonance in these gold nanoparticles. And from that, these surface plasmons can then liberate electrons to flow through this tin oxide nanowire as a current, which we can easily measure. But so how do we make these devices? So we start off with a silicon wafer, like you see here, and we deposit a thin layer of aluminum oxide using a process called atomic layer deposition. We can then place some of our tin oxide nanowires onto that substrate, and these tin oxide nanowires act as a channel for our current to flow through. So this is where electron flow is actually occurring. Deposit some contacts onto that nanowire so we can actually do something with this device. These contacts allow us to make electrical measurements on this device and apply potentials across this nanowire. And finally, and probably most importantly, we can deposit gold nanoparticles onto this device, like you see here. And so these gold nanoparticles act as kind of surface plasmon resonance sites. And so without these gold nanoparticles, we don't really have any surface plasmon activity occurring. And so finally, we can apply a voltage called a gate voltage, which is kind of an influencing potential, to change the electrical properties of these tin oxide nanowires. And so, in particular, this gate voltage can change the conductance of this nanowire. And if we apply this gate voltage while using this device, we can measure the current across this nanowire and use any current readings that we obtain from this device as sort of indications of surface plasmon resonance through this device. And if we do this under various conditions, such as different types of light that we shine on this device, or different lengths of our channel, or effectively our nanowire lengths that we use in this device, then we can learn a little bit more about these surface plasmons and see how we can tune them to our own benefit. So we grow our tin oxide nanowires using a process called chemical vapor deposition. And so here on the left, you see a scanning electron microscopy image of some of our nanowires. And the two important aspects of these nanowires are, first, by working at the nanoscale level, we have a very high surface area to volume ratio, which means that any charge interactions that happen on the surface of these nanowires has an immensely significant effect on these nanowires themselves. And this is not true on the macro scale with normal wires or anything like that. And second, these nanowires are very easily reproduced, which is incredibly important because we need to be able to make devices with these nanowires. And so here on the right, you can see another scanning electron microscopy image of a single oxide nanowire covered with gold nanoparticles. And so these gold nanoparticles range from around 25 to 50 nanometers in diameter, which is just optimal for the surface plasma resonance that we hope to see in these gold nanoparticles. And so the next step is depositing contacts onto these nanowires. And so like I said earlier, we have our silicon wafer with a thin layer of aluminum oxide. That's what you see here, nice top view. We can then place our nanowires onto that substrate. As you can see, we have many nanowires to work with, and they're kind of randomly aligned on this substrate. We can then place a grid over that substrate and deposit a thin layer of titanium, followed by a thin layer of gold, and then remove that grid to obtain a wide array of contacts. And so the idea behind this is that because we have so many nanowires to work with, again, that's why it's important that they're easily reproduced, and we have so many contacts to work with, there's a high probability that any two of these contacts will overlap at least one nanowire, which is what we need to have for a device. And so here you see an actual image of what that looks like. So each of these gold squares represents an electrical contact. And although you cannot see them because they're so small, there are nanowires that exist in between these little gaps here. So we only need two of these contacts to complete an entire device. So simply from this one sample here, we have very many devices to test. And currently, we use this as our testing apparatus. As you can see, it's very beautifully complicated. And this involves attaching probes to these contacts, which are basically little tiny wires that we attach to adjacent contacts like that. And so because we're working on such a small scale, we have to do this all under a microscope. And we do this in vacuum as well because we don't want any air particles interfering with our measurements. And although currently we are facing some challenges with this testing apparatus, mostly because we're working with such small currents around the nanoamp range, we hope to see that we can overcome these challenges and continue with our electrical measurements on these devices. And so as of now, we do have a projection of what that should look like. So here we have a nice projection of the current voltage characteristics of these tin oxide nanowires. So this is without any gold nanoparticles, so this is without any influence of the surface plasma resonance that we hope to see down the road. And so here on the left, we have the current that is measured across this nanowire. On the bottom, the voltage applied, again, across this nanowire. But here we have VGS. This represents our gate voltage, which, like I said earlier, is the influencing potential that we can use to actually change the conductance of this tin oxide nanowire. And so here at 0 volts, you can see that as we increase the voltage, we increase the current through this nanowire up to a certain point where that current saturates. And we see this similar effect at different gate potentials, but you can tell that it's at a much higher current, and this effect continues. And likewise, if we do the opposite, applying a negative gate voltage to this device, we see the opposite happening, and this current decreases up to a certain point where we essentially have no current running through this tin oxide nanowire. And so this idea of applying a gate to this device is important so that we can kind of control the electron transfer with these surface plasmons in our device. And so, like I said, we have successfully completed our devices, and we hope to continue with our electrical measurements once we've figured out a few of our problems with our testing apparatus. But as of now, we hope to, in the future, look at different potentials that we apply to this device itself, so different varying the gate potential that we apply to this device, as well as the different types of light that we shine on this device. So although we'll only be looking at the visible light spectrum because these surface plasmons are created with simply visible light, we would like to look at separate spectra of the visible light spectrum. And finally, we'll be looking at different lengths of our channel. And so we've been doing a little bit of experimenting with photolithography to allow us to actually change the length of our channel here. And we'll be doing these experiments with and without gold nanoparticles so that we can actually attribute any of our results to the surface plasma resonance in these gold nanoparticles. And so on that note, I'd like to thank the entire Moskowitz group for all of their help and support, particularly Professor Moskowitz and my mentor, Jose Navarrete. Also, Catherine for her help with photolithography, and Brian for his help with our LabVIEW programs. Siefe and UC Leeds for allowing me to be here today, for funding my research. And particularly Ophi, Kevin, and Erica for all of their help and support through everything that I've done here at UCSB. And of course, UCSB and the Department of Chemistry and Biochemistry. Thank you.